Statistics man does whatever statisticians can. Let's look at what we've been talking about with the two sample test, and we're going to change it in a second. I want to compare A&M students, UT students, how do they perform on the FE engineering exam, and yeah, the average is higher for A&M, but let's test whether it matters. Here, we've kept them all separate, and this is the test we're used to where the means are separated and these standard deviations are separated. What if we add the assumption that not only are the means equal, the standard deviations are equal too? Why would you want to do that? Well, if we're testing whether it matters which university you come from, you're not just thinking maybe the averages line up, you're thinking maybe the everything should line up because these two groups are not actually that different. And possibly if you're in charge of administering the FE exam, you might agree with this. It doesn't matter what school you go to, when you've learned the information you need, your scores should be the same on average. Well, if that's true, it's going to change the way we look at this. We still want to test whether the means are different, but right here we kept these standard deviations different. In other words, the data from A&M was used to calculate the standard deviation at A&M, and the data at UT was used to calculate the error for UT. If we think they should be coming from the same population, then we would want to pour all the data together to try to get some unified form of what that error should be. So what I want here isn't S1 and S2, I want some pooled version. To pool things means to throw them all together in the pool. This is going to be the same number as that one, and it's going to use all the data to try to get this pooled standard deviation. It's also going to change our degrees of freedom, but let's talk about that in a minute. If I wanted to combine all my data together, here the standard deviation is 4, here the standard deviation is 6. What should the standard deviation be if we threw it all together? Probably somewhere in between those two numbers, but not evenly between them because we have lots more data pulling towards the 4 than the data that's pulling towards the 6. So this guy should be weighted a little heavier. How do we weight things properly? I'm going to calculate this pooled standard deviation based off of the error from group 1 and the error from group 2. So I might be tempted to just add them, but you cannot add standard deviations. If I wanted to add them, I would need them squared first. But right now we haven't accounted for the fact that this one has more data than the other one. So let's multiply each of them by their degrees of freedom. That way this guy is going to have a little more weight because he has more data. We still want to divide by the overall amount of data, which is our n1 minus 1 plus our n2 minus 1. And for some reason, every time people talk about this equation, they just simplify this to be n1 plus n2 minus 2. I'm not sure why that's important. I think it's nice to see you've got each degrees of freedom added together. But when we're done, what we have are variances because we squared them to add them up. So to get back to a standard deviation, we're going to want to square root it so we're back to a standard deviation. Now, if this seems confusing to you, here's a couple little quick notes to remember. Quick notes. Here's a couple of notes that seem quick but take a long time. Oh man, that's not enough. Ha! So, here is our S1 squared. Remember, S is from this equation. So if you square it, we're getting rid of the square root. If we multiply it by n minus 1, then it cancels with this n minus 1. So really what this equation is saying is take each data point minus its mean and add all those up across both groups and then divide by the degrees of freedom for both groups. For this example then, to find the pooled standard deviation, here's my 180 minus 1 times this s squared, the 60 minus 1 times 6 squared, over the 180 plus 60 minus 2, which gives me a 4.578, right in between the 4 and the 6, but a little closer to the 4 because it had more data. Down here we have the matched pairs standard deviation, which is useless because this isn't a matched pairs question. So doing the hypothesis test t-score, I would put in that 4.578. Both places here, same number. And the math people are saying, you could simplify this by pulling stuff out. I'm showing a pattern, so I'm not going to simplify this. You can play around mathematically, that's up to you.
You're making this harder than it needs to be.
But you don't know what you're doing.
but the same number here and here, not split differently on the two groups. The rest of the hypothesis test is going to flow the same way it always has, except our degrees of freedom are going to be different. It's going to be this piece right down here for the degrees of freedom. It's really the degrees of freedom for both groups added together. So 179 plus 59, that's the degrees of freedom that goes right here. And that's the degrees of freedom I used in the applet to get the p-value, which I had to double because this is a two-tailed test, reject the null, and now we say that the averages are not the same across schools.